Dear classmates, welcome to the VLSI testing class. Today we are going to introduce Logic Built-in Self-Test, Part 1, Test Pattern Generator. This is a general architecture of chip-level built-in self-test. We have a test pattern generator, which is TPG, and also we have an output response analyzer, ORA. For today's lecture, we are going to focus on the test pattern generator. Linear feedback shift register, or LFSR, is a very often used component in built-in self-test. An LFSR is a shift register consists of unit delays, which are flip-flops, and the feedback, which are inclusive OR gates. There are two useful applications of LFSR. Number one is for test pattern generator. This LFSR does not have any external inputs, such as this example. This is also called an autonomous LFSR, ALFSR. A second LFSR has an external input, just like this example. This one is often used for ORA. Please note that in this LFSR, the addition sign here represents an inclusive OR gate. There are two popular types of LFSR. Type 1 is called standard form LFSR, also called as external inclusive OR LFSR. We are going to focus on type 1 today. This slide shows an example of a 4-degree standard form LFSR. In this example, every square represents a flip-flop. There are 4 flip-flops in this example. And we also have 2 feedback points to the inclusive OR. The output of LFSR is feedback to the leftmost flip-flop. There are 2 ways to describe this LFSR. Number 1 is the characteristic polynomial. This is the most popular way to describe LFSR. For this LFSR, the characteristic polynomial is x to the power of 4 plus x cubed plus 1. The degree of LFSR is equal to the degree of the polynomial, which is also equal to the number of flip-flops in the LFSR. A second description for this LFSR is to describe the output sequence. Let's say the output sequence is AT. So this output is AT plus 1 because it's a time-shifted version of AT. This output is AT plus 2, this is AT plus 3, and this is AT plus 4. So we can write this equation. AT plus 4 is equal to AT plus 3 inclusive OR AT. Please note that in Mod 2 arithmetic, addition is actually the same as inclusive OR. So 1 plus 1 is 0, 0 plus 1 is 1, 1 plus 0 is 1, and 0 plus 0 is 0. There is no carry in and no carry out in Mod 2 arithmetic. This slide shows a general architecture for an n-stage standard form LFSR. In this LFSR, we have n flip-flops, denoted from left to right by Qn-1 Qn minus 2, Q1, and the Q0. The characteristic polynomial can be written as summation I equal to 0 to n hi x to the power of I, where hn are the coefficients of the feedbacks. Starting from the left to the right, we have hn, hn minus 1, hn minus 2, all the way to h0. Each coefficient is equal to 1 if there is a feedback exists. Otherwise, the coefficient is equal to 0. Please note that for the leftmost coefficient hn and the rightmost coefficient h0, they are both equal to 1. We can write a matrix representation for this standard form LFSR. On the left hand side, this column vector Q plus represents the next state of the LFSR. On the right hand side, this column vector Q represents the current state of the LFSR. In the middle here, we have a companion matrix. In the middle of this companion matrix, we have an identity matrix, where all components are 0 except the elements on the diagonal line. This identity matrix represents the shift operation of LFSR. So Q0 plus is actually equal to Q1, which is a right shift operation. On the bottom row, we have a row vector of the feedback coefficient. So actually, we can write this into Qn minus 1 plus equal to summation hi qi, which is the function of the inclusive OR gate. The characteristic polynomial f lambda is actually equal to the determinant of Ts minus lambda I. So here is an exercise for you. For this example 4-stage LFSR, please verify that the companion matrix Ts can be written as a 4×4 matrix, where we have a 3×3 identity matrix, and in the last row we have a feedback vector. You can also verify that the characteristic polynomial is actually equal to the determinant of Ts minus lambda I, which is lambda to the power of 4 plus lambda cubed plus 1. Now we are going to solve an important problem for LFSR. Given an LFSR architecture and given a test pattern, we want to find the initial state of the LFSR, which is also called the seed. Let's say, for example, we have a 4-degree LFSR with the polynomial x to the power 4 plus x cubed plus 1. The initial states of the LFSR are Q3, Q2, Q1, and Q0 from left to right. We are also given a scan chain. Their bits are S0 all the way to S9 from left to right. The bits of the scan chain are specified by our ATPG. Given this test pattern, we would like to find out the initial states of the LFSR. We have two methods. One is cycle by cycle tracing. The other one is system of linear equations. So let's start from the cycle by cycle tracing method. Suppose that the test pattern desired is 1 x 0 1 x 1 0, where x represent don't care bits. This test pattern is generated by ATPG. So our job is to find out the seed for the LFSR so that we can apply this test pattern to the circuit. Let's say we model this problem by a matrix. Starting from time 0, the bottom row here represents the LFSR seeds. We know that at time 0, the first bit shifted into the scan chain is actually equal to S9, which is 0, and the value here is actually Q0. At time 1, the bit that is shifted into the scan chain is equal to S8, S7, all the way to the top. At time 9, we know that the last bit shifted into the scan chain is S0. So our job is to fill out this matrix. Due to the shift operation of this LFSR, we know that the value of Q0 at time 9 is actually equal to the value of Q1 at time 8 because of this shift operation. Also, we know that the value of Q2 at time 7 is equal to the value of Q1 at time 8. We can work all the way down on this diagonal line. Every bit must be the same. Since we already know that S0 is 1, so every bit on this diagonal line must be 1. Similarly, since this bit has been specified to 0, so every bit along this diagonal line must be 0, and every bit on this diagonal line must be 1. In addition, we also know that due to this shift operation, at time 6, Q3 is actually equal to the inclusive OR of Q3 at time 5 and the Q0 at time 5. So since we already know that this bit is 0 and this bit is 1, we know that this bit is 1. So Q3 at time 5 must be 1. Similarly, we can work all the way up here. We can fill up this diagonal line. And then we continue to the next page. We can apply the same equation and solve that x3, this variable is actually 0, we can also find that x2 is actually 1. Since this is 0, this is 1, we can also solve that x1 is actually 1. So we can now fill up the whole matrix in this way. The last row 1110 is actually our seed. As you can see, this process is very slow. So can we do better? Let's introduce the system of linear equation method. We can actually model this problem as a system of linear equation. In this equation system, we have 4 variables q0, q1, q2, and q3 to solve. On the right hand side, we have the column vector of specified bits. On the left hand side, we have a matrix that represents the system of linear equations. Starting from time 0, we know that q0 is shifted all the way to the bottom of the scan chain. So S9 must be equal to q0, S8 must be equal to q1, S7 is equal to q2, and x6 is equal to q3. After that, because of this inclusive OR operation, we know that Sn is equal to Sn plus 4 inclusive for Sn plus 1. So we can know that S5 is actually equal to X9 inclusive for S6. So we have X5 equal to Q3 inclusive or Q0. We have this equation. Similarly, we can produce the other equations in the same way. Totally, we have a linear equation of 4 variables and 10 equations. So, how can we solve these linear equation systems? Starting from the last equation, we can see easily that Q0 is actually equal to S9, which is 0. Q1 is actually equal to S8, which is 1. And we can also see that for this equation, we can know that S5 is equal to 1, which is Q0 inclusive for Q3. Since that we already know Q0 is 0, so Q3 must be 1. Similarly, for this equation, we can know that S4 is equal to 0. So Q3 inclusive or Q1 inclusive of Q0 must be equal to 0. This is consistent with our previous solutions. Eventually, the top equation S0, which is equal to 1, is equal to Q2 inclusive of Q0. So we can solve that Q2 is equal to 1. Finally, the solution is 1110. However, this is a very slow process. Can we automate this process? In this slide, we are going to show you an automatic way to derive the linear equation systems. Let's say we start from an identity matrix 4x4 identity matrix I. And the row vector T is equal to the feedback row vector, which is H3, H2, H1, and H0. We will work iteratively from the bottom up, starting from k equal to 4. Row k is actually equal to T, the row vector, times the matrix of the previous 4 rows. For example, when we multiply T by the identity matrix I, we get row 4. And then we multiply T by this 4 row, we get row 5, which is equal to 1, 0, 1, 1. We can continue to work this way. Eventually, we will get a system of linear equations that has 10 rows and 4 columns. So, how can we solve this system of linear equations? We can actually use the Gauss-Jordan elimination method. But this time, we will use mode 2 addition. Continuing from the same example, we will append the specified bit to the last column. This is also called the augment matrix. After that, we will remove the useless rows with X. Those are don't cares, but we don't need to solve them. And then we will try to solve this system of linear equations by Gauss-Jordan elimination. To start with, we check the first row. Since this is a 0, so we cannot pivot on this row. We need to find a non-zero row to start with. So we exchange the first row with the second row. Starting from this matrix, we can now use Gauss elimination to solve the solution. To find the solution, starting from the first row, suppose the first element is the pivot element. We want to eliminate this extra 1, so we add row 1 to row 3. In this way, we make this element to become 0, and this would be 1, this would be 0. By doing so, this one becomes the only one in column 1. Similarly, now the one in the second row is now the pivot element. We don't need to do anything because there is only one single one in this column. Now we work on the third row. We need to eliminate this one, and also we need to eliminate this one. So we add row 3 to row 1. We also add row 3 to row 4. After that, this one becomes the only one in this column. Eventually, we will get linear equation system like this. So we know that the solution is 1, 1, 1, 0. Overall, we know that the number of equations depends on the number of care bits in your test pattern. Also, the number of variables is equal to the LFSR degree. If we have more care bits than the LFSR degree, then we may not be solved it successfully every time. Although this time we are lucky, we don't know if we are so lucky every time. So, is there any way that we can guarantee to find a C successfully? This is a good question to answer. So let's answer this question in our class. Thank you. Bye bye.